Hello everyone. In this video, I am going to cover chapter 7, which talks about the internal forces. So first thing first, the design of any structure member requires finding the forces acting within the member to ensure that the material can resist these loads. So for example, if we want to determine the internal forces acting on the cross-section B at point B, we'll first need to determine the support reaction force at point A and point D. And we talked about it in the past, pin support at D. D is a pin support, and then roller support at point A. So, so we can do our equations of equilibrium to figure out the reaction force at AX, at AY, and then DX and DY as well. Secondly, after we do the free body diagram and our equation for the entire structure, and then we're going to move on to do our imaginary cut. We are going to do the imaginary cut where you want to find out where the internal force is. So this problem right here, we are interested in what's going on internally at point B. So we're going to do our free body diagram. We're going to do our imaginary cut at point B. So the free body diagram that we're going to do will include the internal force acting at B once you do the imaginary cut. And then we do our equation. So in two-dimensional cases, typical internal loads are normal force, which is acting perpendicular to the section, normal force perpendicular to the section. Secondly, you have shear force, which is acting along the surface. And then you also will have a bending moment. Keep in mind that when we do our cut at any section, so the diagram here shows at section B, we do our cut, you will have equal in magnitude but opposite direction of the internal forces. The normal force, shear force, and the bending moment, they are going the opposite direction in two different sections. And this is because if you want to connect these two sides back together, reconnect it, the net load needs to be equal to zero if you put them back together. So that's why they're equal on the magnitude and opposite direction. Steps to determine the internal forces. We're going to take the imaginary cut at the place that you're interested in, and then decide which resulting section or pieces will be analyzed to whichever side will be easier. We're going to use that side to do our analysis. And then step number 2, we're going to determine the support reaction force for the entire structure. Pin support, roller support, whatever is going on, we figure out the support reaction force for any unknowns. That's referred to the entire structure. After we done the free body diagram and write our equation solving unknowns for the entire structure, we move on to step 3. Step 3 is when you do your imaginary cut. When you do your imaginary cut, we're going to add the normal force, shear force, and the bending moment to that cut. And then step number 4, after you do your cut, we do the free body diagram and solve for the unknowns for the internal loads. We take a look at some examples together. This one right here, 3 kips per foot, it's distributor load. We know that we learned in the past how do we convert that into a single load and a single point load, and the location of that single point load will be in the middle of this thing because it's a rectangle. So magnitude will be the area, which will be 3 kips per foot multiplied by the distance over here. It's being applied over the 6 feet. So it'll be 3 times 6 gives me 18. So 18 kip is the magnitude, and it will be right in the middle of the 6 feet. That's where that 3 and the 3 on the left on the right comes from. Okay. Now we know that point A is a roller support, so you have reaction force AY only. Point B is pin support. You have BX and BY because it's a pin support. It's got the horizontal constraint as well. And then we're going to write our free body diagram. Again, this is referring to the entire body, entire structure, entire beam. Sigma Fx equal to 0 tells me that support reaction at B horizontally equal to 0, Bx equal to 0. And then vertically, we'll hold up to that vertically, we're going to do a summation of moment about point A. A is an unknown, and then summation of moment about point A. Since Bx equal to 0, we can solve for the value of By. And keep in mind that whenever we do this, counterclockwise, we define it as negative. So apparently we're doing a summation of moment about this point right here. Okay, that 18 kip is trying to rotate the beam about this direction. That is, this is counterclockwise. That's why this thing you have 18 times 3, which is positive. Moment arm is 3 feet for that 18. And then the second thing is your by. By is trying to rotate clockwise, and clockwise is defined as negative. And you have negative by multiplied by the moment arm, which is 9 feet. That's where that comes from. So you're solving for the value of by. And then now we solve for the bx, by, and then ay. We know all of them. We're going to do our imaginary cut. Since what we're interested in is the internal forces at point C, so we are going to do our imaginary cut at point C. Now looking at the distributed load on the left, I think it's easier to do our free body diagram analysis on the section on the right. The section on the right says that I have C, once I do my cut, I have my normal force, which is NC, shear force, which is VC, and then the bending moment MC. Now, again, we assume all these directions. You just assume a direction. And then if your result come out to be positive, meaning your assumption of the direction is correct. If it come out to be negative, it means it's the opposite. It means it's the opposite of what you originally assumed. So there, we do our sigma fx equal to 0 gives us nc equal to 0. That means there's no normal force. And then we do sigma fy equal to 0. That will help us solve the shear force at C. Vc equals negative 6 kip. Negative sign again, it means the actual direction of the shear force is the opposite than we were originally assuming in our free body diagram. And then we do our moment that gives us our bending moment equals negative 27 kip foot. That means 27, the MC, the direction of that MC moment, C bending moment at point C is the opposite of what we originally assumed as shown in the free body diagram here. Right, so next problem, we looking for what's going on internal force at point C. So pin support at point A, roller support at point B. We know that you have AX and AY at point A and BY only at point B. Next, we're going to write our equation. Sigma fx equal to 0 tell us help us solve the value of ax. Sigma mb moment about point B equal to 0 will help us solve for the ay. Okay, and then after that, we are going to pick our section. Since what's going on with the pulleys and etc. looks slightly more complicated than the right side looks slightly more complicated than the left side. So we're going to do our analysis just on AC. Once we do our imaginary cut, we have an imaginary cut at point C. We do our shear force, we do our bending moment. Normal force, shear force, and bending moment. Sigma fx help us solve the normal force. Sigma fy help us solve the shear force, and we do summation of moment about point C help us solve the bending moment at point C. And again, if it's negative, it means the direction is the opposite than we originally assumed. And if it's positive, it means that yes, this your originally assumed direction is the correct direction. Last group problem here, we're looking for what's going on at point C again. Now, at the bottom for this problem, you have a distributed load. It's 15 pounds per foot. That means we have 12 feet total. We're going to multiply 150 times 12, give us the total magnitude of this force, which is 1,800 pounds. And the location of it will be right in the middle of this entire beam. 18 feet total. That means it will be 6 feet right there in the middle. That's where that comes from. Okay. And then A, we know at point A is a pin support. It's a reaction force. You have AX and AY. We do our sigma moment about point A to help us solve the tension of this cable. And then sigma Fx equal to 0, solve for AX, sigma Fy equal to 0 to help us solve it for AY. And then since we're interested at point C, we are going to do our imaginary cut at C. Now notice that we replace the distributed load for the entire beam at the bottom to be 1,800 pounds. And notice that when you do your cut, it's not like you can skip it even if that cut is only 3 feet away from the from point A, from the pin support A, and then you're replacing that 1800 point load to be the distributor load is 6 feet away. That does not mean when you do your imaginary cut at point C you can just ignore the distributor load. It's still there because it applies throughout the entire beam. So other words, so when we're looking at the distribute load, when we do our imaginary cut, it will be this portion right here. It will be this rectangle here. Okay, so it's still the same density, 15 pound per foot, multiplied by the distance, and this time the distance will be 3 feet to get the in order to get the area to get the magnitude of the equivalent distributor load once we do our cut for only section AC. So you have 150 multiplied by 3, which gives you 450. That's where that comes from. And the locations of it will be in the middle of that 3 feet. That's where that 1.5 and that 1.5 comes from. Okay. Next thing is that reaction force, AX and AY, we calculated from the previous slide, AX, AY, when we calculated when we looking at the structure entirely, do the free body diagram in the equation. You have your AX and AY, and then when we do our imaginary cut, we calculate the normal force, shear force, and the bending moment. Again, we assume a direction. If they come out, the magnitude come out to be negative, that means it's the opposite than we originally assumed. If it's come out to be positive, then cool. It's the same direction as we assume. So we have our three equations. So sigma fx equal to 0, all the force horizontally equal to 0, sigma fy equal to 0, all the forces vertically adding that together equal to 0, and then summation of moment equal to 0. This will help us figure out the shear force, the bending moment, and then the normal force at point C, internal. This is all I want to show you in chapter 7. Thank you for watching.